So this is an interesting conference. It's different to the sort that I come from normally, and I think that's what makes it exciting, because you've got people from different areas. And I thought it would be helpful for you to understand what I'm going to talk about, to understand where I'm coming from, right? So the tripod illusion is apposite, not only because we're being recorded, but because one of the first autonomous machines ever envisaged was 2,500 years ago by the Greek Hephaestus, where he envisaged these automatic tripods that would do work for you. A tripod is just a table, right? It's a better design for a table because it works on a floor that's not even flat. So I'm a machine learning researcher. I've developed algorithms and theory, things like the one-class SVM, right? And interestingly, I see the next talk is about anomaly detection. It shows you something. This algorithm was developed 15 years ago. You're starting to see these things being used more widely now, right? Keep that in mind. I'm currently the CEO of NICTA, so I have a broader view of ICT, and that's an interesting thing. But I've also been, for the last 2 years, doing a project which I've learned a lot from on technology for Australia's future. So I was asked with some other people to try and look into the future about technology, generally, not just ICT, and what would its impacts be, how would it change society, what might one do about that if you're a government. So what I want to do in this talk is to take those diverse backgrounds and synthesize some perspectives that might stimulate your thinking on things. I'm giving analogies and questions. I'm not telling you any answers, but when I come to a talk, I like talks with questions. If it's an answer, it's already done. There's nothing to do. So what is technology, right? This is a conference on predictive technology. So technology, there's zillions of definitions, but effectively they help us do stuff, right? The thing on the right's a washing machine, okay? You're going to see lots of old pictures here. It dates from the 16th century, right? So it's not quite automatic, but it doesn't work just by hand power. You see the water wheel in the back? That's the motive source. The clothes go in the thing, this cursor work here, and they get squished backwards and forwards, right? This thing's a large vertical lathe. So, you know, you often see these things, and we tend now, we're stuck in the present, it's all shiny iPhones and so on, but technology is everywhere around us. This building is technology, and I'm going to reflect a lot on that. And technologies are a means to an end, right? You don't build a washing machine just because it looks cool, right? Even if it was built by Apple, you wouldn't build it just because it's cool, right? You'd build it to wash your clothes, right? And you always got to keep that in mind, that there's a purpose for these things. And different technologies have things in common, right? And what I'm going to try and do is to draw some analogies between all of this old stuff and the leading edge technologies that you folks are in the process of creating and deploying. All right, so that's my message. Predictive technologies can learn from older technologies. So what do we mean by predictive technology? So predictive technologies, even that narrow class, that is far from new, right? And what I'm going to be doing here is, I thought it would also be interesting to draw your attention to some literature you might find interesting that I've discovered in doing this project. And so you'll see all of these books, which I've found fascinating and I've pinched stuff from. So automation and control, the way you control things, the way you control people in society, machines, animals, your agriculture, this pervades the development of humanity. Right? And this lovely book by this communications theorist talks about that, right? So it's the control revolution, the origin of the information society. So he tracks through all sorts of things and views many technologies that you would not think of as a technology, right? So advertising, right? I'm not talking about computational advertising, just the concept of advertising, that's a technology, right? And he talks about its introduction and, you know, the impact that it's had. So you can't control a system without trying to predict where it's going to be. Right? That's the premise. My microphone's failing.
Yeah, I'm just using this one to grow.
How's this? Is that on?
I don't know.
They're all off. Okay, so it's downstream. I will just project, but you probably lost the recording. Here's a couple of 19th century innovations that I thought were interesting. So this is a programmable API. I know that's recursive acronym syndrome, but this is the Jacquard loom, right? So the guy programming it. Here's another innovation that I thought was a really new thing, but it's actually old. So this is a mail sorting rail car. So in the US in the 19th century, so Universal Postal Service was one of the most revolutionary information communication technologies, right? It's a packet switch, you send all your messages all around, it's delivered in the form of paper. And what is this carriage? Well, rather than sending all of the packets to a central place to do the sorting, they had this idea that if you distribute the system and you take the computation to the data, so the guys there are running a sorting algorithm, and you do that in the rail car itself. Right? So I thought that was a pretty cool analogy if you think of the leading edge way we think about computation and so on today. Anyway, prediction is central to control, I said. So here's an early example of that. So Sperry Rand's a famous company that makes gyroscopes and so on. Gyroscopes are used for controlling, where machines point and so on. This is a very early automatic gun sight, right? So if you want to shoot something, right? So it's easier to shoot something if it's not moving. If you want to shoot something that's moving, what are you doing? You are predicting where that thing is. Right, so, it's another early example of predictive technologies. Microphone's working again. Another interesting aspect that I'll come back to is new technologies are scary for people, okay? So, here it's not quite autonomous, but people perceived it that way. If you can see the front of the railway train, it's got this nasty face on it. This is like an autonomous train about to be let loose in the suburbs of New York. Right? So think of the autonomous cars that are coming. And here is the dangers of doing your shopping online. Right? So it wasn't kind of via the web, but it was the same idea delivered via earlier technology, which was the mail order catalogue. Okay? You remember when the first online commerce came on, there's lots of sharks out there and there's lots of people got burned. Well, again, it all comes around. Predictive analytics for ads. So this is just an extract from the book I mentioned. So again, you think, oh, this is leading edge, right? It's just at the turn of the century this stuff really took off. That's true. At the turn of the 20th century. Turn of the 20th century, people were doing predictive analytics for ads. Of course, they couldn't do it in this fine-grained fashion as we're doing now. So what's the point of all of these examples? The point is it's very easy to get into this mindset that everything we're doing now is new. It's not. And that's not to say that what we're doing now is not valuable or cool or worth doing. Absolutely not. But it is worthwhile reflecting how things have changed in the past. So if you think about technologies and technological change, you think about how do they change and what is the natural rate of change? Where do the technologies come from? So one common myth is that technology is applied science. Now, many school courses will teach you this, that the scientists figure out the principles and technology is merely the application of the science, right? It's a great story, right? It has this linear notion to it. School teachers love it. It's just wonderful in every respect except that it's false, right? The empirical reality is that it is false. In almost all cases, the technology comes first and then the scientists figure it out, okay? The science of thermodynamics arose after people built heat engines. Okay? And the same thing's going to be true today. You folks are building stuff that you probably don't know what you're doing, and I'm not insulting you there because if you knew what you were doing, then it's not research, right? I'm complimenting you. You don't know what you're doing, but you're building it anyway, and that's the way that technologies develop. And then over time, the scientists, people more like myself, will try and figure out some principles and neaten and tidy it up. And in 20 years' time, when we teach our kids, we'll tell them a big fib. But it will help them understand it, right? So I'm not trying to say we're doomed and we're doing everything wrong. Now, another interesting common pattern that you see, and now you've got to remember that a lot of this is just in our heads rather than out there in the world, it's a categorization, is if you think of technologies in the broad sweep of history, the economists have come up with this phrase, it's rather obvious meaning, of general purpose technology. So you all would have heard of the Industrial Revolution. You dig into history, and historians will talk about several successive industrial revolutions. You can go overboard on this, and there are these fancy theories called Kondratiev waves that explain the cycles of the economy and so on. I wouldn't go that far, but I think it's fair to say that you can identify the impacts of the first revolution, which was steam power, the railway, electricity, reticulated electricity, and then computing, right, to pick a few, right? You can always pick some other ones. You can say, well, you know, why not get more specific? Now, they've all driven industrial revolutions, but the graph that I'm showing you here shows you an interesting fact about how long it takes, right? Which, again, we often forget with our perception that time is somehow moving faster. So what's plotted here are two curves, and you're looking at the percentage penetration. Now, I can't remember the precise definition from this graph. I think it's sort of like households that have a computer versus households that have reticulated electricity. And you do it years following the arrival, the first instance, right, that you can definitively say, okay, we've developed electricity, or we've developed a computer that you can go and put on a desk. And you look at the time here, it's very similar. And there are reasons for that, right? I mean, part of it is just generational. You need the current kids to grow up with the technology expecting that it's part of the world, and so they demand it rather than thinking that it's something magical. So you see these patterns, and things take time, so that's worth keeping track of. The speed is not constant. So another generic fact that you learn from the study of this stuff is that depending upon the interrelationships between things, things can go faster or slower. And typically where there is infrastructure, right, this can slow you down, right? So you think of the infrastructure that modern predictive analytics requires. You know, there's the computational power, there's the network connections and so on. You've got this deep stack, you know, you're operating here, but there's a stack below you that you want to rely upon, okay? So one lovely definition of infrastructure is something that you only notice when it breaks, okay? So things like if the electricity went out here, we would find that highly anomalous. We've come to rely upon it, right? We really would be surprised. The fact that the stupid computer connection didn't work reliably, we also expect that. And what does that tell us? That this isn't infrastructure yet. 20 years' time, that will work. Right? There won't be all of these different standards. There's a prediction for you, right? It's like the power outlets on the wall. There is a standard, which by and large just works perfectly well, right? You don't have conflicts with plugging things into the wall unless the power point's mounted on the floor and you've got some gigantic transformer you're trying to stick in. So anyway, the other thought that I want you to keep in mind here is infrastructure, right? So there's a vague question I can pose. What is the infrastructure that you need? How do you build it? I'm going to come back to that. Now, going more generally, asking how does technology change, you can say, well, okay, it's not just applied science, it somehow moves along in some fashion. How can you describe that? So in all of the work that I did for this report, the far and away the best metaphor that I found for how technology changes is evolution. And it's not just a metaphor, it's actually a lot more precise than that. So often people will misunderstand this. They'll say, oh, well, there's biological evolution, we understand that, and you're just drawing an analogy with how technologies change. And yeah, you can go and do that. Now, this itself is not a new thing, right? So Darwin's theory was presented in 1868. The first presentation of technology as an evolving system was 1869, right? So again, you know, it's not a new thing. But what have we got here? Not goal-directed. There's no one in charge. There's no one person in charge here. There's a source of variation. So again, in biology, you get that from random copying errors in the genotype, right? So here, it's lots of people just have different random ideas and try them out. You get recombination, right? You can combine different ideas together. More of that soon. And a source of selection. What's that? Well, we can just think of it as the market, right? Lots of technologies get developed. They all seem fine, right? Even particular instances of it. Some of them work and some of them don't. And when I say some of them work, some of them get adopted. It's not that they're necessarily better. Like, for all I know, the Microsoft Zune was just as good as the iPod. right? Technically, it probably was, right? And everybody could be carrying Zunes around, but they don't, right? Random chance, right, by and large. As a consequence of this is my point, as a consequence of this, it's unpredictable, right? Because of these factors, it's very hard to predict out more than a few years how technologies will change. If you could do that, you'd be a squillionaire, right? You'd know which technologies are going to fly. So one big difference, however, between the evolution of technology and the evolution of biological organisms is the prevalence of hybrids. Okay, so this is from a famous book by Alfred Kroeber. He's the grandfather of anthropology, father of the science fiction author Ursula Le Guin, if you want some useless extra facts. But he was talking about the difference between natural evolution and cultural evolution. Technology is a cultural artifact, and this is the tree of life for species. You don't get species splitting apart and then joining back together again. Extraordinarily rare in nature. It's the default with technology, right? And this is worth thinking about, and it's worth thinking about in terms of when people get obsessed about originality, right? So I'm running a research lab, people want to do a new thing, okay? This tells me being obsessed about novelty for its own sake is the wrong thing, right? There is never a new thing. There is always new combinations of old things, which over time we give a label, and hey presto, we've got a new thing, right? So that's my model of technological change. Now there's some other common patterns that recur in technological change, and they go by these jargony words I've put up the top. So again, this is largely come from economic historians who are kind of less vested in the creation of the technology, and they can kind of step back from afar and try and look at it. So the technological inertia, it's a rather obvious metaphor. You know, you have the inertia of a large object, it's hard to get it moving, or if it's moving in a certain direction, it's hard to change it, right? So once technological change develops a certain momentum, it's hard to move, right? So whether you call it inertia or a momentum. And there are various reasons for that, right? So one of the reasons is just the power of vested interests. So if you currently distribute your energy to a city through gas, and you've invested lots of money in all of the pipes for that, and this newfangled energy distribution technology called electricity comes along, you're going to do your darndest to resist it, right? And they did. The gas companies managed to delay the introduction of electricity, right? And now, reticulated electricity from large central power stations is the default way we generate energy. And there's this new way of doing it where you can co-generate on top of your house and feed it back in, have fancy market mechanisms. What's going to happen? The centralized distributors are going to resist it. Of course they are. Right? So you can see these patterns, right? And, you know, it's useful to know that they occur. Apart from anything else, it might help you stop being so disheartened about the difficulty that you have in making some change. There's also interdependence, right? So this is particularly apposite for this community, right? So you'd know perfectly well the problem of writing large bits of software where you have all of these dependencies. So the software community is very explicit about that, but it occurs in all manner of technologies. You know, the less the dependence that you have, the faster you can adapt, right? We all know that, but it's interesting that it applies to artifacts other than software. So another phenomenon that the economists talk about is path dependence and lock-in. So, you know, the most famous example is the keyboard. So here's a keyboard I saw in Paris a few weeks ago in the Museum of Arts and Sciences. I would hate to have to type on that. I don't know if you can see the letters. I don't even get how this works, right? Because, you know, here's a key that's got a capital J and a lowercase u, right? Here's one that says M2. This is X/, right? It just defies imagination that someone would think that's a good way to lay out a keyboard. But there you have it. And the round thing, that's obviously driven by the implementation, right? You know, they had to write it in COBOL, and that's just the way it came out. So, but The QWERTY keyboard, of course, right? We all think of that as just a given, but it was just one of these design choices. And, you know, it's as bizarre as anything else. And in fact, one of the reasons, arguably, as to why we've got the QWERTY keyboard is that salesmen could pick out the word typewriter just by using the keys on the first row, right? It's daft. How about that? It's just marketing after all. So let me talk about the prediction of technology. So I've told you some of the difficulties. Now, you would all have heard of Moore's law. There are lots of analogous the general fancy word we used for these was hypotheses of technological progress. All right, I don't know how else to say it in simpler words, but a picture makes it simple. Here I'm plotting the cost of producing polyvinyl chloride per pound over time, and also the annual production. I'm also plotting the cost in US dollars per megabit of DRAM and the volume. And you see these curves, and it's a reasonable bet that you could just extrapolate them, okay? And if you did so extrapolate them, you probably would not end up being wrong. I mean, Moore's law has been a good guide. Now, there's several reasons, at least two reasons for this. One is, it's probably true that there's lots of little effects that gradually make it more and more effective, so, you know, it just would happen anyway. The other thing that happens is it becomes a self-fulfilling prophecy, and Moore's law in particular has turned from just a prediction to a strategic roadmap for the semiconductor industry. Either way, the prediction holds true. Now, here's the thing. You can have that level of predictability about the technological components, but you cannot predict the impact. So this seems hard for many people to understand how that could be. So just because the price of producing a transistor on a chip goes down does not allow you to predict Facebook, right? You just can't do it. Who's to say in advance what things will work, what things will not, right? People predicted in the 60s that all telephones would be videoed, in the late 60s. We can use video chat now, but most of the time we don't, right? You'd only use it for your girlfriend when you're overseas or something, right? It's not widely used. 3D TV, okay? So when was 3D TV first introduced? Any guesses? 30s. Yes, first working prototype. It was crap, right? And when was it predicted? And at that time, in 1937, there was a report written where the authors said, yep, this will be big. 10 years' time, all TVs will be three-dimensional, right? And even now, people are backing away from it because, they did user studies. The BBC famously did a user study. They wanted to try a few broadcasts of 3D content, and so the program they decided to show in 3D to, get people excited about was the Queen's Christmas message. No, this is true. You can look it up. And there wasn't a lot of uptake, so I'm not making this up. I can give you the reference. So they're backing off from it. So being able to predict the impact is very difficult. And when I say this, I mean there's actually empirical evidence, right? So this report that I've done, we've tried to dig into the evidence in detail for all of these things. And so this chap, George Wise, apposite name, actually did a whole PhD on the accuracy of technological forecasts. And he collected, 1,500 forecasts made in the past, right? So they were made a long time ago. And now here we are. Their future time is our past, and so you can check how well they've done, right? So you all work with prediction, you know how to do a cross-validation or something, so this is what he's done. And guess what? To quantify this, he said, let's try and get predictions where you're predicting a binary outcome, because otherwise what loss function do you use? Well, you would be better off using a coin, right? That's the sad reality. You average across all of these experts, and There's a list here. These slides will be on the website. I haven't put them up yet, so you can go and read this yourself. These are not nincompoops, right? There's people like Henry Ford, Norbert Wiener. In fact, Wiener, who's one of my heroes, was appalling, right? 14%. So he made 7 predictions, 6 of which were wrong. Right? It's the grandfather of cybernetics. So they're very hard to predict. They're even hard to retrodict. So this was something that was even more surprising to me. So when I started this work, I thought, okay, it is indeed hard to predict the future, but at least the past we can explain. But even that is incredibly controversial, right? So there was this famous book, the one on the right, Railroads and American Economic Growth. So everybody knows, right, that the promulgation of railroads through the United States in the 19th century led to enormous growth of the American economy, correct? We all know this, right? So this chap, Robert Fogel, said, well, hang on, is that really true? What if we didn't have railroads? What would have happened? Well, what would have happened was that the other technology for using goods and for moving goods and people long distances, namely canals, would have been extended. And he actually worked all of this out, right, in detail. He worked out where the canal network would have had to have been extended to. He calculated how much it would have cost. He calculated how much extra time it would have cost the farmer to go on his horse and buggy to the canal. And he went and calculated all that through and then worked out what diminution of GDP there would have been in the US by 1890 if there weren't railroads. 1%. Right? Now, many historians quibble with this, and as they should, because it's, doing this counterfactual thing, like if the Nazis won World War II, what would we be doing, right? How on earth can you do that? But it is interesting to think that through, right? So it goes to show that even the things that you think, for sure, ARPA made Facebook, right? Sounds plausible, but maybe it's not true. Understanding impacts is difficult because they are so multitudinous. So there was this report, Recent Social Trends in the United States. You probably can't see the date there, but it's 1933. Recent, of course, is relative, right? At the time it was recent. And there was this newfangled information technology called radio. And the sociologists that wrote this chapter made a list of all of the impacts that they reckon radio would have. Now, what I find interesting about this, right, is how different it is to the stuff you'll see in newspapers today. I hope there's no journalists here. I'm not picking on you. I'm just, as an empirical fact, the stories that you'll see about the impact of a new technology now are typically, it's going to be this. This technology will have this effect. These guys I like because they had 150 different effects, right? It just kept on growing. And some of them are really funny. Letter writing to celebrities, a widespread practice, right? Used in submarine detection. Well, yes, actually. Home duties and isolation more pleasant. So none of these are ridiculously wrong. Most of them are unfalsifiable, like they're not quantified, but, they're right. And this was right. I used to have a ham radio station when I was a kid, so that worked out. So I want to talk about a few other things. So systematization of machines, right? So you have all of this technology, it's big, it's complicated, it evolves, it's a great big mess. What do the biologists do in the face of that complexity? They classify, they build taxonomies. And people do that for machines. So I've got several great books, like this one here, 507 Mechanical Movements. Right? You can buy these for a few dollars. And they're just fabulous. They're just catalogues of all of these components, right? It's components. And what is the point of this? It's compositionality. You want to build a machine that takes wheat, grinds it up, turns it into some pellet or something or other. You're going to use a whole range of these things. It's a catalogue. And you start to see that, of course, with software, but it's interesting to reflect the way that this is laid out and the implications that it's had on the evolution of mechanical technology. One extremely important development of technology that is particularly appropriate for this group is the development of interchangeable parts, right? So I know this is hard to read, but this is an advertisement for a wrench, Right? This dates from about 100 years ago. And in the fine print down the bottom, it makes the point as something special, because it was unusual at the time, that the parts of this wrench are interchangeable. So, you know, you're looking puzzled. You think, well, surely, yes, aren't they always? Like if the little thumb screw breaks, I just get another thumb screw. That was a major invention. It's one of the most powerful inventions in technology, right? The invention of interchangeable parts. It's usually attributed to people like Eli Whitney or others in the US about manufacturing guns. Turns out it was actually done in France even earlier, around the time of the French Revolution. What's the idea? The idea is that if you're building a machine, every part needs to be interchangeable, right? Rather than, as a craftsman, you go and fit them all together. And this, I thought, was interesting. This, I reckon, is the first unit test, right? This is a set of tools. If you're building a gun, you manufacture a given part and you see whether it fits. It literally is a unit test, right? Rendered in steel. Anyway, that's what I'm calling it. So we take it for granted that there's lots of machines, and you know, the only way that you can build complicated machines is to deal with this modularity. This is a Harvard Business School professor who wanted to understand why Silicon Valley worked so well, right? And in a nutshell, her answer was modularity. Right? You have lots of different companies focusing on single individual bits. They can specialize and it all gets plugged together. Now, there's plenty of theories about why Silicon Valley is so special, but the modularity and the ability to glue different components together seems paramount. And it allows you to build computers, right? Like, you know, here's an early computer. It's actually a rebuild of, it's not even a rebuild, it's a build of the design that Babbage did for the difference engine. Right, this cost $3 million to render in beautiful brass. This is glorious. The nice thing about computers is that you can render it on different hardware, and this is a cheaper version. Right? It still works. Let me talk more specifically about particular challenges for predictive technology. I've got only 8 minutes left. So I encountered this paper very recently, Machine Learning, the High Interest Credit Card of Technical Debt. Which I encourage you to have a look at. You can easily find with that title. And it points out two key things. Well, not this paper doesn't, but I'm building on another talk that I've heard. There's this modularity, the development of APIs, it separates concerns, right? You can consider this thing without having to worry about that thing. That's how you write code. That's how you build complicated machines. What's different about predictive technologies is that you have to train them. And so, as this paper makes the point, you train on certain training data, and that's like a hidden global variable, right? It's sort of under the radar. You've gone and built your face detector for certain classes of faces or certain lighting conditions. And no software engineering frameworks really capture that, right? It's not like a library dependency or something. So I don't think we've got the right metaphors for this yet, but I think it's an interesting reflection. How to do experiments is another thing, right? So if you go and build a sorting algorithm or something, right, it's relatively straightforward to figure out how to write the unit tests. Predictive technologies, that's much more challenging. And I maintain that part of the reason is that oftentimes you don't know what it is, what problem you're trying to solve. So that's another lesson from technology more generally. If you don't know what it is you're trying to do and you're just building the thing, then how are you going to know whether you succeed? So in the community I come from with machine learning researchers, this is quite a legitimate gripe that I have, right? That people will build these things, they think they know what they're doing, but they can't really articulate it in terms that the end user cares about, right? You might say, oh, well, I can just evaluate the area under the ROC curve, right? That's a measure of performance of a learning algorithm. But what about in terms of what the bank actually wants? Anyone that tries to use machine learning technology to solve some real problem grapples with this problem. How you translate the technical requirements of performance to what the customer actually wants. And we don't have the science for that yet, so I think that's a new area. And I've used this slide in many talks because I really like it, but it shows you my view of a lot of machine learning technology at the moment. It's a bunch of hammers. So the book, The Evolution of Technology, has this collection of hammers in it. It's from a larger collection of hammers that someone catalogued in Manchester in the 19th century, 5,000 different hammers, right? They're all highly specialised. This one here is a hammer specifically designed for making butter casks. It's just a little mind-blowing. There's other hammers. These are imaginary hammers. There's this great book, The Catalogue of Impossible Objects. This is a hammer for confined spaces. And this is a glass hammer for delicate objects. Okay? So when you're writing your algorithms, you know, which hammer are you building? And so at the moment, you know, I've talked about past technology and it becomes industrialised at a large scale. I think we're at the stage where it's still a cottage industry. And you guys are trying to industrialise it. You're trying to transform it, right? And you're trying to repeat what was being done for all manner of other technologies. I'm going to skip that. And the reason you want to do that is that the only thing that people really want in the end is a system. So everyone knows who this is. It's Iron Man, right? And you realise that this is a work of fiction, right? You didn't know that, right? So I can tell you how. Here's how you know that this is fiction, right? Because in the movie, Tony builds this thing himself, right? It takes like a day or something, right? Right? This would be like 1,000 man-years or something to build a machine that complicated. And this is, of course, the way we work, right? And it's precisely because we have to interwork together that you need standards, right, and APIs. So that's why you have it. Now, I'm preaching to the choir here, I realise. But I'm trying to think of, you have standards, like, you know, the mechanical things I showed you before, the nuts and bolts. There's standards there. You get standard-sized nuts and bolts. What do standards mean for predictive technologies, right? Now, at one level, you can think that the particular API that you write, that is a standard. In a way, it's an implicit standard. But, you know, if you try and say, well, what is it you're trying to achieve with a standard? So I think this is a really difficult question. And I've thought about this from my own perspective on the science of machine learning, about just forget about rendering this stuff into code, just trying to understand what you're trying to do. And my starting point is motivated by these two quotes. So the first guy is Jorge Luis Borges, famous Argentinian novelist. And the guy at the bottom is Gregory Bateson, who's an anthropologist. And his point is that you have to look at the relationship between things. So I've done that with machine learning functions, machine learning algorithms. There's a question for you. With the predictive APIs, what exactly is it that you're trying to standardise, and how do you relate the different standards to each other? I'm going to skip that, and because James is going to give a talk on this, so you'll hear all about it. There's a couple of other challenges that I think are paramount in the area that we're working in: privacy, security, and all that. And the one point that I'd make there, the picture at the top right is from a colleague of mine in NICTA, which shows all of the data mining services that suck personal data out of an Android phone, right, for all sorts of reasons. And, you know, there is this challenge about the security and privacy of data. What I haven't seen in our community is very much response to what I think of as an extremely important report that came out in the US a year ago from the Presidential Council of Scientific Advisors on big data, its threats and opportunities. And they maintain a point that was developed at MIT, which is that it's no use trying to secure the data because you can't. If the NSA can't keep their secrets, who can? Right? Now you think about it. But what you can do is you can control the use of the data, right? And there's good arguments for that. And I think this is worth thinking through. When you're building these predictive technologies that can do all of these amazing things, who are you serving? Whose interest are you serving? And what are you doing with it? Rather than, you know, who controls the data. It's an interesting perspective. I'm skipping a couple of things because I'm almost out of time. So I'm going to just get to my conclusions. I'm sorry I couldn't do the demo. If anyone's interested, I can demo predictive spatial analytics thing that we've done from NICTA. So predictive technologies are technologies, obviously. You can learn from the past. So this interesting book by David Edgerton, The Shock of the Old, is just solely focused on how much of our modern world is influenced by technologies that were developed a long time ago, right? We forget this. We still build buildings out of concrete, right? It's hundreds of years old. It's incredibly energy intensive, right? Surely there's something better. People are working on it. Technologies for data, generally considered, but predictive technologies in particular, I would conjecture will be the next general purpose technology. It's the next industrial revolution. I think it's that big. It will take a long time, right? People in the midst of the industrial revolution didn't think, they didn't wake up one morning and says, oh, yep, the industrial revolution, it started, right? It was a label given to it 50 years afterwards, right? So there's a conjecture. Standards can be good and bad, right? So this is one of the key takeaways I would want to impress upon you. The reason standards are good is for interoperability. So this is a book written by 2 professors at Harvard Business School about the general notion of interoperability, and the subtitle is The Promise and Perils of Highly Interconnected Systems. Very interesting to look at. They do a lot of interesting case studies on things like shipping containers, how that came about, how you ended up with the sizes that you've got. Mobile phone chargers. So it turns out that the EU had to threaten manufacturers on this. They effectively said, if you guys don't standardise this, we will do it for you. And then the industry said, no, don't do that, we'll get our act together. And nowadays, most phones, with the exception of Apple, are charged through a standard USB port. Right? And the last point, second last point I'd leave you with is that there is a notion that the economists have come up with of a gateway technology. So often when people think of standards, they want to standardise everything, right? And, it's just overreaching. The things that seem successful, the successful evolution of standards, are where you do it narrowly. Lots of little standards that can interoperate in an ecosystem rather than one massive standard. And the economists identified this notion of a gateway technology. So this paper, The Economics of Gateway Technologies and Network Evolution, Lessons from Electricity Supply History. There was DC power. There was AC power. They're incompatible. Someone invented a machine that could convert AC to DC and back again. And then it doesn't matter. That's the key point. Then it doesn't matter because you can convert. Now, there's still efficiency gain losses, but it's an interesting point. So these minimal standards, a good analogy, I think, is from this science fiction book by Neil Stephenson, The Diamond Age. So they set in the far future, there's all sorts of crazy stuff, but there's this notion of a common economic protocol. It's the bare minimum that you need for different societies to work together. You've got these very vastly different societies, but there's a minimum that is standardised, and then they can interwork. So I'll leave you with some other challenges that I see. The technological impacts are not equal on everyone. Some people will benefit enormously and some will be harmed, right? And I would maintain that it's the technologist's responsibility to think about that. And you will see, you just have to open a newspaper now to see the terror that many people have of robotics, right? And they think that this is coming no matter what, right? They think this stupid Terminator robot will come, right? They've seen the picture, they've seen the movie, and it's going to happen, right? It is not going to happen. It's only going to happen if people make it happen. Now, why would you do that? Why would you build a killer robot when there's so many other valuable things to do? So I think we've got a moral responsibility there. And I'm now going to stop because I think I'm over time.